The first topic that we need to review is graphing, both exponentials and logs. We graphed our exponentials and logs by an XY chart. So for number 1, we would want to create an XY chart where we're going to choose some X values. I'm going to choose -1, 0, 1, and 2. When I plug in a negative and an exponent, creates a reciprocal. So it's going to take that 3 and flip it over. It makes 1/3. 3 to the 0 power is 1. 3 to the first power is 3. And 3 to the second power is 9. And we want to plot those points. -1, 1/3. 0, 1. 1, 3. And 9 would be up off the top, so I'm not going to worry about plotting that. Domain and range. Domain for an exponential is all reals. We can plug in any x value we want. It will become very large very quickly, but we can plug in any x value we want. Our range is limited though. We're never going to get anything below the asymptote. That asymptote exists at 0 in this problem, so we are only going to get values greater than 0.
Does it ever flip to y is less than 0?
Yes, if we had a negative multiplier in the front of the function, it would be a lower half function, so then it would be less than 0. For question 2, the first thing we want to do is take care of the shifting that appears there. What does the +2 do to the graph? Left 2. When it's with the x, it goes sideways and backwards. So we're going to go to the left 2 for that. And what does the +1 do? It goes up 1. So we're going to go left 2 and up 1 to create the new center of this graph. Then we want to make a chart for the parts of the function we didn't shift. So we shifted the +2, we shifted the +1, so we want to make a chart for y equals 3 to the x. Which is rather convenient because that's actually the chart we already made for number 1, so we don't need to make it again. We can just plot those points, but we want to plot them from where we shifted the center of the graph to. So from where those red lines meet, we want to go -1, +1/3, over 0, up 1, and over 1, up 3. So we get the same exact graph that we had in number 1, except it's moved 2 spots backwards and 1 spot up. Domain will always be all reals for an exponential function. And what about range on this one?
Y is greater than 1.
Greater than 1. So we had an upshift of 1. That's going to take the entire graph and move it up 1 spot, and it's never going to cross that line at 1. Questions? I can't read the bottom of my fraction here, number 3. What does it say? It's a half? Okay. Alright, so we're going to make a chart for this. -1, 0, 1, and 2 for our x's. When I plug in a -1, that's going to take that 1/2 and flip it over and give me 2. 1/2 to the 0 power is 1. 1/2 to the first power is a half. And a half squared is a half times a half, or a fourth. Plot those, back 1 up 2. 0, 1. 1, a half. And 2, a quarter. So we still have an exponential curve, but this one is different than the other ones because this is an exponential decay because of that base value less than 1. So our graph is flattening instead of going from flat to steep. Domain is still all real, so we can still plug in anything we wanted for x. And our range is above the line 0. Number 4. We're going to make an XY chart. And we have to be careful because in our function, there's already a negative on the x. So when we plug in a -1, we've got e to the -1, which is really e to the first. We plug that in the calculator and we get about 2.7. When we plug in 0, anything to the 0 power is just going to be 1. When we plug in a 1, because there's already a negative in the equation, this is really e to the -1, which is about 0.4. And then when we plug in a 2, because there's already a negative equation, and the calculator will want to do e to the -2, which is about 0.1. We want to plot these points. And we get a graph that looks very similar to the last one. This is a decay because of the negative exponent. The base is bigger than 1, but the negative exponent creates the decay here.
So it's fractions and negatives.
Fractions as a base or a negative as an exponent will create the decay. Okay, and domain and range are same as the last one because there was no shifting involved in the graph. For the last two, we're going to switch and think about logs. Now, when we do a graph of a log, what we want to do is actually graph the exponential, or make a chart for the exponential. So we're going to turn this into the exponential the way that we learned how logs behave. What's the base of the log in number 5? 10. When there's no base written, the base is 10. To rewrite this as an exponential, our equation would be 10 to the power of y equals x. To rewrite a log as an exponential, the base stays the same, but the other stuff switches jobs. Okay, so 10 to the power of y equals x. And we're going to make a chart on that, but since we're kind of doing things backwards here, we're going to choose our y values instead of choosing our x values. Because y is on the side that has numbers with it, so it's easier to plug stuff in over there. 10 to the -1, a negative flips it over, so that would give us 1/10. 10 to the 0 is 1. 10 to the first is 10. 10 squared is 100, definitely not plotting that. Remember, the more extreme our base is, the sharper of a turn the graphs take, whether it's exponential or log graphs. So when we plot these, x is 1/10, so I'm going to go over just a tiny bit. Y is -1 over 1 up 0, and over 10 be like out there. These graphs follow a vertical asymptote. So I noticed on some homework assignments that some of you had this graph kind of continuing out into the negative side there. It doesn't cross by that axis. These have a vertical asymptote that they don't cross. So that means our domain is limited. Since they have a vertical line that they don't cross, we're never going to get anything over on that left-hand side of the graph, which means that our domain is going to be that x is just greater than 0. We're only going to get from the 0 line and over to the right, and never technically even the 0 line. And y will be all reals. It is growing upward, it's just growing upward very, very, very slowly. But it is growing upward. For number 6, the first thing we want to do is shift. What's the +2 do? Left 2, because it's with the x in parentheses. So it's going to go sideways, and sideways always goes backwards. So we're going to go back to the left 2, and we're not going to go up or down at all. So the equation that we're going to work with then just becomes y equals the natural log of x. We want to rewrite this as an exponential. What is the base of the natural log? E. So as an exponential, this becomes e to the power of y equals x. We're going to make our chart, and we're going to choose our y values, because y is on the side of the equation with the other numbers, there's e. And we're going to plug them in. So e to the negative 1 is 0.4. E to the 0 is 1. E to the first is e, which is just about 2.7. And e squared is about 7.4. So when I plot those, I'm going to go over a little bit less than a half and down 1. Over 1 and up 0. Over almost 3 and up 1. Over about 7.5 and up 2. Domain is limited because we have a vertical asymptote we're never going to cross. So what's that domain going to be? X is greater than negative 2. That shift that we made moved that asymptote over 2 spots, and we're never going to cross that line now. Our range is going to be all real cell. Questions on graphing?
So is it when you start using the log and the natural log size non-estimated?
Right. So the log is the inverse of the exponential. So it's kind of like taking those first 4 graphs and kind of flipping them over creates the log graph. So they grow out to the sides instead of growing up. Okay, our next section asks us to simplify the expression. When it asks us to simplify, we're not going for decimal answers here. We still want exact answers. We just want to take care of any power rules or log rules that we can apply. So if I have e to the 4th times e to the 5th, what do we do with exponents when we're multiplying? 9, we add them. And leave it right there. Don't type it in the calculator and get the decimal unless the direction specifically asks for an approximation. We want the perfect answer. So number 8, I'm going to 2 and e to the negative 2. Because that first e is like an e to the first. So when we add our exponents, that gives us negative 2. What can we do with a negative exponent? You can put it down to the bottom of a fraction. So we'll leave the 2 on the top because it's fine. It doesn't have a negative exponent. But that e can go down to the bottom. I would actually accept either form of the answer.
Good.
Now for the next one, what we need to do is remember what is a log asking us. So we know what a plus sign is asking us to do with numbers. We know what a square root sign is asking us to do with numbers. A log is another symbol for us that is asking us to do something with a number. First, what is the base of this log? 10. And the question a log is asking is the base to what power gives us that number. So this is asking us 10 to the what equals 1,000. And what would that be? 10 to the 3rd equals 1,000.
So one like that, if we know then the base, then can we just type into our calculator?
Yes, since that one is one that the calculator could do, you could type that one in the calculator. Number 10, we can't. Has a base that we can't type into the calculator. So this is asking us 4 to the what equals 64. 4 times 16. 4 to the power of 3 then. is equal to 64. Number 11, back to our e's and our power properties. When we multiply fractions, we multiply together the tops and we multiply together the bottoms. When we multiply those bottoms, we're going to get e to the 5th. Adding up those exponents, and then what can we do? Cancel out the e's because they're on top and bottom, the same amount of them on top and bottom. So we're left with just the 5. Common wrong answer here is 4. A lot of students subtract those e's from each other, but this is a division question. So we're dividing those e's off of each other, leaving us with just the coefficient of 5. The next groups of questions on condensing and expanding are using our log properties to either put logs together or to take logs apart. So in condensing, we want to put all of this together. So inside of our answer, we should just have a log written once, and everything should be inside of it. So the first thing we want to do is take care of anything that's not inside of it, anything that's out front. So what do we do with that?
Put it's the exponent.
F as an exponent, so it gives us log of x to the 4th
Times
plus log 8. We still have 2 separate ones. We want them all together. So we want to take that addition and smush it together. And how do we smush together addition?
X plus x to the 4th 8.
Multiplication.
8 x.
Addition becomes multiplication when they get smushed together.
Does it matter which way you put the 8?
No, if you put x to the 4th times 8, that's fine. We just typically write the constant in the front, but I wouldn't mark it wrong. It's still right the other way. So number 13 has some stuff out front to take care of first. So we get the natural log of x cubed minus the natural log of 2 to the 4th. And this one has a subtraction of logs. So in the last problem, we took our addition and we smushed it together and it became a multiplication. What will subtraction become? Division. Oops. So we're going to have 1 natural log with everything inside of it. When you actually have numbers that you can work out, you should work them out. So 2 to the 4th is 16. Okay, the first part becomes the top of the fraction, and then the subtracted part, the part that had the negative, becomes the bottom of the fraction. Our expanding problems here are exactly the opposite. Okay, now we want to separate these out and give each number or letter its own individual log. So in number 14, we have a natural log of 4 times x times y. How do we separate out those multiplications?
Addition.
With addition. So we get the natural log of 4 plus the natural log of x plus the natural log of y. Each of the multiplications becomes its own individual addition.
About 13, do you have to put the ln in the outside? Like, does it matter if you do ln x cubed over ln?
Good question. Most common wrong answer on number 13 is for students to give the ln to both the top and the bottom. That is actually different. They each had an ln when it was subtraction. When we switch it to division, it becomes the ln of the whole thing, not the ln of both the top and the bottom. So that's the most common thing I see students do wrong there, is actually writing an individual natural log for both the top and the bottom. And we don't want 2 separate ones. We want 1 natural log with everything inside of it. Good question. So that it kind of looks then like number 15. And then number 15 we want to separate out now. So what do we do to separate out that division? Subtraction. So we're going to get the log of the top minus the log of the bottom. In the end, we want each number and letter to be totally plain inside. So these are not totally plain. So what do we need to do with those exponents? Drop them down. Take them and move them out front. So I get 3 log of y minus 2 log of x. Questions on simplifying, condensing, or expanding? The next problem asks us to use our change of base property. Our change of base property is that we take the log or the ln of the of divided by the log or ln of the base. Here we do want a log or ln on both top and bottom. It doesn't matter whether you use the common log or whether you use the natural log, as long as you do the same thing for both of them. You type it in the calculator carefully, closing parentheses after that 12. And that gives us about 1.4. And remembering what a log is asking, we can check that answer. That means that 6 to the power of 1.4 should be about 12. Because that's what a log is asking us, is the base to what power gives us that number inside. So we could check our answer that way and make sure that it makes sense.
Can you reduce it?
You cannot reduce it because they're both stuck inside of a log. It's an order of operations thing that we can't divide the 6 and the 12 until we've taken their logs. All right, moving on to some equations to solve. First, we have an exponential equation. 10 to the something equals 10 to the something. Since the bases are both 10, the exponents must be the same. Because 10 to the third has to equal 10 to the third. It couldn't be 10 to the fifth on one side and 10 to the third on the other. Those wouldn't be equal. So if the bases are equal, the tops must be equal. So we can just set those the same and ignore the 10s. Subtract 2x from both sides. And subtract 2 from both sides. If I take that back and plug it in, I get 10 to the 5th equals 10 to the 5th. So that is a true statement. On number 18, the bases are not the same. I have 3 to the something equals 9 to the something. So the bases are not the same, but could we make them the same?
Yes.
Yes. By doing what?
Squared.
Writing a 9 as 3 squared. 3 squared is 9, so we haven't changed the problem, we just changed the way that it's written. Replace the 9 for a 3 squared. Now the bases are the same on both sides, which means the exponents must be the same on both sides. Subtract an x. So we get 4. If we took that back and plugged it in, we would get 3 to the 8 equals 9 to the 4th. And I don't know what those are, but I could type them in the calculator and confirm that they are in fact the same thing to check my answer. Questions? Number 19, we do not have matching bases. Can we write them with matching bases? Now I can't turn a 5 into a 2 to a power. Okay, 4 is 2 to a power, 8 is 2 to a power, but we kind of miss over 5 then. So how do we undo an exponential?
2 squared 4.
It's the inverse of an exponential. A log. Yep, some kind of a log. Any kind of a log will undo an exponential. So we're going to take some kind of a log. I usually do a natural log, but it doesn't matter what kind of a log you do. And we'll take some kind of a log of both sides. I do a natural log or a log base 10, so that then in the end of this problem we can type it into the calculator. Then we're trying to solve for x and it's stuck up in the exponent, but what can we do with an exponent inside of a log? We can move it to the front. So this becomes x ln of 2 equals ln of 5. And we're going to divide by the ln of 2 to get the x alone. Type it into the calculator carefully, closing the parentheses after that 5. And we get about 2.3. We could check that answer, bring it back to the original, and make sure that 2 to the 2.3 is 5. Kind of makes sense because 2 squared would be 4, so we'd expect our answer to be a little bit bigger than that. So we switched gears and we're going over to log equations now. So in number 20, we have a log on both sides of the equation. The bases are the same, so log base 6 of something equals log base 6 of something. Some things must be equal then. Since the logs are the same and the bases are the same, the insides must also be the same. Solve by subtracting 2x from both sides. Add 3. And divide to get 2. We can take it and plug it back in, and we get log base 6 of 7 equals log base 6 of 7. That makes sense. The two sides of the equation are exactly the same then. Number 21 does not have a log on both sides, so we can't just set insides equal because there aren't insides on one side of the equation. So what we want to do to solve a log equation then is undo it with an exponential. So we want to rewrite this as an exponential. To turn a log into an exponential, the base stays the same and the other stuff switches sides. Because what a log is doing is saying the base to what power equals the stuff inside. So the power and the stuff inside switch. So the base stays the same and the other stuff switches. 5 to the third is 125. And divide both sides by 3, and that doesn't divide in nicely, so I would just leave it right there. (22) has 2 logs, but they're not separated by an equals. So this is a different kind of problem than 20. They're separated with a plus. So what we want to do is smoosh them together like we did on the previous page with our condensing properties. So what does addition become when we smush them together? Multiplication. So we want to multiply together those insides so that it's all inside of just one single log instead. So then this becomes like problem 21. The previous problem, we want to rewrite it. So the base stays the same, 3, and the other stuff switches sides. Three cubed is 27, and then we need to distribute that y. Let's subtract 27 to be able to solve the quadratic. To factor this, we want to find two numbers that multiply to make negative 27, that add to make positive 6. So what would those be? Negative 3 and positive 9. Multiply to make negative 27 and add to make positive 6. So the solutions are then positive 3 and negative 9. The opposites of the factors are our solutions. But there's something we're not allowed to do inside of logs, because as we saw in the graphs, they have that limited domain. That means there's certain things that don't work. Just like inside of a square root, there's certain things that don't work. It's actually the same as a square root. We can't take the log of a negative number. So we want to take these solutions and plug them back in and confirm that we don't end up taking the log of a negative number. If we plug in a 3, 3 plus 6 is 9. 3, that one's all good. But if we plug in a negative 9 plus 6 is negative 3, and that's a problem. We can't do that. So that solution is extraneous. We did everything right in solving, but it still just doesn't really work. Questions on solving log equations. Last problem, you need to know a formula for this. You need to know that the amount of money we have is equal to principal times E to the power of rate times time, our PERT formula.
Did you say you have this memorized?
You do need to have that memorized. In that formula, P stands for principal. It's the amount of money we're putting in the bank. So you deposit $1,500 in an account. E is the number E. R is the interest rate as a decimal. Don't plug in 7.5. You will get a ridiculously large answer. And T is the amount of time. Make sure that all of that is up in the exponential when you plug it in your calculator, that there are parentheses around that power, the whole thing, the rate and the time. So you get $1,878.48. So that means after just 3 years of letting our money sit there, we've made $378 and some change. You will notice after this review in your packet, there's about 2 more pages of logarithm practice and review. You don't have to do it. If you want more practice on condensing with logs or simplifying logs, working with log expressions, you can do that for some more practice. There are solutions posted on my website. I think it says like logarithm practice solutions or something, and it's a PDF file. So if you want to practice those and check your answers, you can do that. If you're missing any of the homework from Chapter 8, you'll want to work on that to get that into me tomorrow as well.